In section 2.3, we're going to get down to the nitty-gritty of taking limits of various types of functions. And in order to do that, we need to familiarize ourselves with a group of limit laws. And they start right at the beginning of this section of 2.3. And wait, there's 5 right off the bat. I'm just going to list all of the limit laws here, and then we'll start doing examples. So the first one just says that, now this is all under the assumption, very, very important you remember this, that the limit of x as x approaches a of f of x and the limit as x approaches a of g of x exists. So we're looking at a couple of functions, and we're told that the limits as x approaches a particular value a of these two functions exists. So if that exists, then we have these limit laws that hold. The first one says that the limit of the sums is the sum of the limits. So if we take the limit of f of x plus g of x as x approaches a, we can get the same thing by taking the limits individually and adding the results. The limit as x approaches a of f plus the limit as x approaches a of g. That makes sense. That makes sense. The second one says the same thing is true for subtracting. That if we take the limit of the difference of two functions, that's the same thing as taking the difference of the limits. So we take the limit of the first function as x approaches a and subtract from that the limit of the second function as x approaches a. The third rule says that if we have the limit as x approaches a of some function times, some constant c times our function, well, then we can move that constant out front. We can say it's the constant then times the limit as x approaches a of f of x. So take the limit of a constant times a function. That's the same as taking the constant times the limit of the function. 2 more to go here on this first set of 5 limit functions. The fourth one rather, says that the limit as x approaches a of the product of two functions, f of x times g of x, again assuming that both of those limits exist, is equal to the product of the limits. So the limit of x approaches a of f times the limit as x approaches a of g. And finally then, the same thing holds for the quotient on number 5, the fifth limit law, which says that the limit as x approaches a of f of x divided by g of x will be equal to the limit of each individual thing, the quotient of the limits, we would say. The limit of the quotient is the quotient of the limits. So limit as x approaches a of f of x divided by the limit as x approaches a of g of x. However, we have to assume that the limit as x approaches a of g of x not only exists, but it exists and is not equal to 0. Because if the limit as x approaches a of g of x is 0, well then, my friends, we are dividing by 0, and that's no good. Now, continuing on, there is a product law, which is basically a repeated application of rule number 4. If you multiply a bunch of things together, if you take the limit of two functions multiplied together, that's the same as the product of the limits. Well, if you do that for numerous times, the function multiplied by itself numerous times, we get law number 6, which says that the limit as x approaches a of a function raised to the nth power. So we're taking the limit of a function multiplied by itself n times. We get the same thing as taking the limit of the function first and then taking that result times itself n times. So again, the difference here between these two sides of the equation, the first one you're taking the function, multiplying by itself n times and taking the limit of that resulting function. You get the same thing as if you just take the limit of the original function f and then take that result by itself n times. Okay, and then there's a couple of, well, kind of obvious, I guess, if you think about them for a little bit. The 7th rule says that if we take the limit as x approaches a of a constant, we get a constant. Well, that makes sense. The constant function is always that particular value, and so it's always going to be c, so no matter what you're approaching, no matter what a is, the limit of a constant function is always going to be that constant. And the limit of the linear function y equals x, well, it's just going to be a. The limit of x as x approaches a is just going to be a. That makes sense as well, I hope. Alright, a couple more here then. I think we can squeeze a couple in here. The 9th rule given in this section is that the limit as x approaches a of x to the n is equal to a to the n. So a power function, since it's defined and continuous, for all real numbers, well, then the limit of a power function as x approaches a will just be the power function evaluated at a. In other words, a to the n. And the same thing is going to hold for a root function. The limit as x approaches a of the nth root of x will just be the nth root of a. So in these particular cases, we can just plug a in for x to get our limit, because our function, in the first case x to the n, in the second case the nth root of x, is defined and continuous for all values of a. However, if, as the book points out, if n is even in this 10th rule, then we assume that a is positive, because the function itself, the nth root of x, if n is even, is not defined for values that are 0, for values that are negative. So that means that the a value has to be positive, so that we can come at it from both sides, the left and the right. The last then of the numbered limit laws says that if we take the limit as x approaches a of the nth root of f of x, this is kind of like the power law that we looked at before, that's going to be the nth root of the limit as x approaches a of f of x, where n is a positive integer. So in other words, we can take the nth root of a function and take the limit of that. We get the same thing as taking the limit of the function and then taking the nth root of the result. And again, a parenthetical note here that they mention in the book, and it's worth mentioning, and that is that if n is even, then we assume that in order for this rule to hold, the limit as x approaches a of f of x is positive. Again, because we can't take the nth root of a negative number if n is even. Now, a couple other rules that are mentioned in this chapter, and then we'll start looking at some examples called the direct substitution property. And let's take a look at what this says. We talked about this a little bit in 2.2, and that is basically if our function is defined and continuous at a particular point, then the limit of the function as it approaches a is going to equal just the value of the function at that point a. And so here it says it a little more precisely: if f is a polynomial, or so a polynomial, remember what those are, or a rational function, so that's just a polynomial divided by a polynomial, rational function, and a is in the domain of f. Well, if it's just a polynomial, then a is always going to be in the domain, because for a polynomial function the domain is all real numbers. But for a rational function we have to make sure that the value a does not make the denominator 0. If that's the case, then the limit as x approaches a of f of x is equal to f of a. In other words, for a polynomial case, suppose f of x is 2x squared minus 3x plus 4. Well, this function is defined for all real numbers. There's no points of discontinuity, so it doesn't matter what our number is here. The limit as x approaches, say, 3 of f of x is just going to be f of 3. It would just be the same thing we would get if we would plug 3 into our function. Alright, so there's one example. The rational function example, if we have, say, g of x is 3x minus 2 over x plus 1. Well, we could say then that the limit as x approaches, say, 2 of g of x is just going to be g of 2, since 2 is in the domain of this function. Now this rule would not hold, and so it would just be 3 times 2 minus 2 over 2 plus 1. Now we could not say, however, that the limit of g of x as x approaches negative 1 is equal to g of negative 1, since g of negative 1 is undefined, because negative 1 is not in our domain. It makes the denominator 0. So that's why we had to make sure that a is in the domain of f for the rational function case of the direct substitution property. And it says that if we have a function f of x and it's equal to g of x for all values at least when x is not equal to a, then the limits are going to be the same. The limit of f of x as x approaches a is going to equal the limit of g of x as x approaches a. And remember, when we're looking at the limits of functions as x approaches the number a, well, we're looking at values of x that are close to a. We're not actually looking at the values of x that equal a. We're only looking at what happens to our function as we get closer and closer and closer to a, not what happens to our function when we're equal to a. So as long as they agree on everywhere except a, well, then their limits are going to agree, provided the limits, of course, provided the limits exist. Okay. Now there's a theorem, Theorem 1 on 12, which we talked about a little bit actually in 2.2, that says that the limit as x approaches a of f of x is going to be defined and equal to L, and that's going to be true if and only if the limits from both sides exist. The limit as x approaches a from the left of the function is the same as the limit as x approaches a from the right of the function, and those equal L, and those agree. So that's something we talked about in 2.2, and that seems to make sense. A couple more theorems then to look at. Theorem 2 tells us that if we have two functions f and g, and f is consistently less than or equal to g, at least for values of x near a point a, and the limits of those two functions exist as x approaches a, well then the limit of the function f as x approaches a will be less than the limit of the function g as x approaches a. That makes sense since, again, f is consistently less than or equal to g, while the limit then of f is going to be consistently less than or equal to the limit of g as x approaches a value a, assuming those limits exist. And that leads us then into the final theorem and the final statement from this section, and that is a very important theorem called the squeeze theorem. It's Theorem 3 in your book. And the squeeze theorem basically says that if we can come at a function from both sides, then that thing's going to be stuck in the middle. So let's take a look at it. What it says is if we have three functions and f is less than or equal to g, g is always less than or equal to h, and that's always going to hold for any x's, at least x's near a, and the limits of f and h exist. So the lower one and the bigger one, they exist and they agree, they're both equal to L. Well, then you can see it's going to have to be the case since g is stuck between these two functions, and these two functions have a limit that is the same, namely L. G is stuck in the middle, and you have to squeeze h and squeeze f on g. G is going to be squeezed down into L as well. Just looking at an illustration of this, let's say we have our three functions. F here, it's the smallest of the three. H of x is always bigger or greater than or equal to the other two. G of x is stuck in the middle. Well, if f of x and h of x have a limit that agrees at a point A, and again, h of x is always bigger than or equal to g of x, f of x is always less than or equal to g of x, g of x is going to have no choice but to be stuck in the middle there and have that same limit. The limit of g of x is also going to be the value of the limit of f and h. So that's what the squeeze theorem says. Alright, that's it for this video. In the next video we will look at some examples from 2.3.